Morning. Morning, everyone. Welcome to day 2 of F8. Today's a fun day because we get to talk about the future. Mark last year introduced our 10-year roadmap, talking about the products and the platforms and the technologies that we're going to be rolling out over the 3, 5, and 10-year time horizon. And here on day 2, we get to dig deep into that 10-year part of this roadmap to talk to you in detail and geek out about our 3 main pillars for the future: connectivity, AI, and VR and AR. I'm going to give you a quick overview of how we're doing on these things and what progress we've made since the last year, and then we have tons of great speakers after to go through each of these in great depth. Let's kick it off and talk about connectivity. Our goal here is simple. We want to figure out how to connect the 4.1 billion people around the world who aren't currently connected to the internet. In order to do that, we're investing in all sorts of radical new technologies that have the promise of dramatically reducing the cost of delivering internet access throughout the world. A couple of examples of progress we've made in the last year: Telegraph is our multi-gigabit wireless backbone system designed for the urban core. So instead of digging up a street and laying cables, you just put these things up on telephone poles. You can actually see a few of these just a few blocks away from the stadium here in San Jose, where we're piloting our first network. Millimeter wave has the promise of delivering backbone internet wirelessly at high performance over long distances. We've set several world records in transmission of data. We've gone up to 36 gigabits per second over a 13-kilometer link wirelessly. And last year, we introduced to all of you Aquila, our high-altitude, long-endurance vehicle for providing internet access via the sky, the upper atmosphere. And at that time, we were in scale model testing, and we've since commenced full-scale flight testing of this full-scale prototype. Now, these are just 3 of many of the component technologies we're going to need to connect the world. And in order to do this, it's going to take years, and it's going to take help and collaboration from you, our partners, and community. And speaking of community, this is one of the most exciting parts about how we're doing our connectivity efforts, is everything we're doing to try to spur collaboration and cooperation within the industry. As an example, we released Voyager, our first white box transponder and router for open packet optical networks. And we released Open Cellular, a design for a cellular base station, which is open source hardware and software designed to make it more cost effective to provide cellular internet access, especially in regions where this is scarce. And these are 2 of many of the projects that fall under the umbrella of the Telecom Infrastructure Project, which boasts more than 450 participating companies, telecom providers, operators, technology companies, all of us collaborating together to figure out how to build technology that's cheaper and easier to deploy so that everyone around the world can get connected. And of course, we've been doing the same in the data center for years with our Open Compute project, where we're collaborating and building next-generation, high-performance, low-power consumption data center equipment so that everyone can build the internet services that will ride on this network. And we have over 200 members of the OCP project. Now, I'd love to talk to you in a lot more detail about these projects, but luckily, Yale McGuire, who runs the connectivity labs, will be up later today to go in detail on some of these and some other projects we're doing. Now, AI, part of our 10-year vision, has been a big part of F8 so far. And yesterday, Mark was able to show you a really compelling vision of what the AI-powered AR camera can do. And I got a chance to talk to you a little bit about the progress we've made in computer vision, an important field of AI. Now, computer vision is just one part of the overall puzzle for AI. Our goal for AI isn't just to teach computers to see. We want to build truly intelligent systems that understand the world and are useful for all of you and the things you want to do every day. And in order to build those sort of actually intelligent AI systems, we need to do more than just perception or teach them to see. We need to solve problems on teaching computers to learn and understand the world around us, the context of the world we're operating in. We also need to teach computers to do something all of you do every day. It's predict the future, to understand what's going to happen next with this bottle of water. And we need to teach computers, once they see and understand and can predict, they need to plan, to figure out when they need to turn to not crash, or how to answer the next question you're going to ask when you ask the question from the bot. And when you fuse multiple fields of computer vision, of language understanding, of parts of AI together, you start to get some impressive results. Last year, one of my favorite applications of computer vision for us was being able to auto-caption all of the billions of photos shared every single day on Facebook. So anyone with a visual disability can have a better sense of what's in the photos on Facebook. And this on the left here is what this looked like last year in 2016. With upgraded computer vision, and by fusing that computer vision with upgrades in the language understanding technology we have in AI, we're able to start giving you much more natural captions, as you can see on the other side of the screen here. We can use verbs, we can describe what's happening in the world. And this is awesome, and this is great progress. But computers still really don't understand a lot about the world. Hungry yet? I know it's morning time, not the time to eat a pizza. But let me ask you this. Is this a vegetarian pizza? Anyone? It is a vegetarian pizza? I heard a lot of no's. Okay, why is this not a vegetarian pizza? Okay, it has pepperoni on it. Why does pepperoni make it not vegetarian? Okay, it's meat. Pepperoni's a meat. Why does meat make it not vegetarian? Because vegetarians don't eat meat, right? Okay? Now, when did you guys learn what vegetarianism was? This morning? Last month? Decade ago? Someone said college? Gary? Maybe multiple decades ago? Or are we forgotten? But just think about what 2,000 people in this room did. I ask you a totally out there question. None of you were prepping on eating habits before you came to a day 2 F8 conference. All of you instantaneously said, well, vegetarians don't eat meat, pepperoni's meat, it's not a vegetarian. Easy question, why is the CTO boring me on day 2? Computers are confounded by these questions because they don't understand the world around us. They have to learn about it, and they have to put this information together to answer questions that we really care about. This is why, with all the promise of AI, so many of the bots and assistants we have seem to not be able to answer most of the questions we ask them. And so we need to go beyond computer vision. We need to teach computers to understand the world. 2 years ago at F8, I put together a presentation about this set of 20 toy word problems we'd constructed in the Facebook AI Research Lab. These are word tests that you might take in elementary school. And at the time, no existing state-of-the-art AI system could solve them. In the intervening 2 years, the Facebook AI research team and the broader research community has come together, and we now have systems with 10,000 training examples that can answer all 20 classes of these problems. These are pretty simple problems, and you can see them on the screen. So it's time to make these problems harder. We're now training systems that can ingest all of the English articles within Wikipedia, 5 million articles, and answer any question that may be answerable from Wikipedia. This is not referencing any other sources. This is not humans hand coding and putting that data into a structured form. It's taking unstructured text and then answering any questions you may be able to get from that text, kind of like a reading comprehension test you might get in school. And it's these sort of problems that are going to teach machines and teach AIs in order to have the sort of knowledge, understanding, and reasoning we need to build truly intelligent systems. And we're building new data sets. We found that building data sets is a great way to spur creativity in the community that require you to combine and fuse perception and computer vision with reasoning, understanding to answer much more complicated questions. And so solving these problems is critical to making our bots and assistants helpful in the tasks that are really important. I ask you, right now or when you go home, ask your bot of choice any one of these questions and tell me if you get satisfactory answers. Simple questions. Who should I go see Fast and the Furious 8 with? Can't help. But these are the sort of questions that are important. How do I connect with my community? Which friends should I reach out to? How do I find a club? How do I go volunteer? What should I do in my career? These are the human questions that matter, and our bots are pretty darn far away from being able to do that. And this is why we're so excited about investing in not just computer vision, but all of the fields of AI that combined together can start to build these sort of intelligent systems. Now, I could spend 2 hours talking to you about AI, but luckily we've got Joaquin, who leads our AML team, our applied machine learning team, coming up a little bit later today to do an even bigger deep dive. Our third pillar is VR and AR. Now, we heard a lot about AR yesterday and the AR camera, and you got to see the demonstration of Facebook Spaces. I wanted to give you an update on where we are with VR. It's been a big year for VR. Last year on this stage, Oculus Rift had just started shipping. We hadn't yet shipped the Oculus Touch. And since that time, we've shipped Rift and Touch and gotten in the hands of consumers and developers all over the world. And the great thing about these platforms is you get them in the hands of people, and then you can see the amazing creativity that happens. Tons of awesome games, from Ripcoil to Robo Recall to Job Simulator to The Climb, where I can climb a mountain, are out there and are amazing fun. But what's also been cool is how much people have been creative with non-gaming applications of VR. These applications include sculpting in 3D, painting in 3D, exploring worlds that I could never go to, like a fly-through through the International Space Station. Or even more impressive applications, like a team in São Paulo, Brazil, the Walk Again project, who's been using VR and BCI to help rehabilitate patients with severe spinal cord injuries. Or a team in the Children's Hospital of Los Angeles that's exploring using VR to help train physicians for the stresses and rigors of working in an emergency room. Or a team at Stanford who realized that teaching medical professionals the intricate understanding of how the human heart works and how it would perform after various surgeries is challenging because of how 3D that piece of anatomy is. And so instead of using paper and books, they're exploring using VR, where you can interactively go and see what different repairs look like. So when you're caring for these patients post-surgery, you know the best course of treatment. And of course, yesterday, we launched Facebook Spaces. And it's already been awesome to see how much fun people are having, interacting with their friends, sharing media, and being themselves in VR. We are one of the few, maybe the only, company who's investing in VR across the spectrum. We're investing in the high-end and PC. We're investing in research. We're investing in content, in platforms, and software. And yes, we're also trying to drive adoption by building systems that are easy to use and low cost. We've been working closely with Samsung for years, and they're just about to ship their Samsung Gear VR controller. And the idea of the Gear VR controller is to capture some of the magic we've seen in the Oculus Touch controller and bring it down to a much more affordable price point. To give you a very qualitative sense of this is one of the more popular titles in Oculus Rift. It's called Dead and Buried. On the left, you have the title in the Oculus Rift, our product. That's amazing, $600. On the right, the same title that we've ported to the Gear VR and the Gear VR controller. That system, if you're buying it from scratch, is $130. Requires a phone, but if you have the phone, $130. And as you can see, it's not the exact same experience, but you capture much of the magic, and this is just a whole lot of fun. And this is one of many applications we're seeing coming out with the Gear VR controller on the Gear VR platform, coming out now. Dozens of titles coming out, running on the Oculus platform, leveraging our investment in software and infrastructure. Now, video has been a huge part of how people use VR. People are sharing tens of millions of 360-degree photos and videos on Facebook. Here's a sample of some of the more popular ones. You can look at the Northern Lights. Of course, Mark's daughter, Max, adorable, first steps, seen over 10 million times. And then drone heliskiing, which I didn't know was a thing until I saw this video. Now, capturing 360 immersive videos, yes. It is awesome, there you go. Whoever thought we'd be showing this? Capturing 360 immersive videos is something we want all of you to be able to do. So as part of that mission today, everyone attending today's F8 is going to get a free Gyroptic IO 360 connected camera. This allows you to plug into your iOS or Android device and instantly share or live stream your moments in 360 immediately on Facebook. So enjoy. I can't wait to see the content you share, because as we've seen in Facebook Spaces, it's one thing to look at these awesome videos, it's another to have something your friends or you have created and shared. And that's where it really comes home. Now, video is designed to be immersive. For years, we've been trying to build videos that made us feel like we were there. And we started out with black and white, moved to SD and HD and Ultra 4K HDR video. And I've just talked about the amazing amounts of 360-degree 2D videos available on Facebook. But these aren't yet all the way to indistinguishable from being actually there. So we wanted to push the immersion chain. And last year, we said one of the missing links was to get 3D 360 videos so that in VR, it felt like you were really there. And we launched the Surround 360 Open Edition camera. This is an open hardware and software platform, 17-camera rig designed to capture phenomenal 360 3D content. And by releasing this, we've unleashed the creativity of the community. It's been awesome to see manufacturers clone this camera, copy it, use our stitching code, use our calibration code to build all sorts of different rigs, and more importantly, to shoot lots of great content. This is an example of the quality of content you can get off of the Surround 360 V1. It's shot in Grand Central Station, and it gives you that ability to feel much more closely like you're there. Feel the 3D environment, see the expressions on people's faces. Yes, and get photos taken of you while you're recording. But we're not done yet. We're not fully immersive. There's more we can do. So we want to push the immersion chain further. One of the challenges of 360 3D photos is when I view them in VR, if I happen to move around, if I move to the left a little bit or move forward, the world is still locked. It's still locked wherever that camera happened to be placed. And so we want to fix that problem, and we've been designing the second generation. This is the X24 and the X6. These are cameras designed in partnership with FLIR, who's been working with us to integrate their camera modules into the center of them. But what we've done is we've done a camera layout specifically designed to maximize pixel overlap at every single part of the scene, not just around the outsides, but in every part of the sphere. And what that pixel overlap does is it allows us to take our expertise in computer vision and go to town. We can get a very detailed per pixel depth map of every part of the scene that you're capturing with this camera, which starts to break into this ability to solve this 6 degrees of freedom problem. What do I mean by this? This is what I mean. You place a camera in a fixed position. This is this camera, the Surround 360 prototype shooting actual content. I place it in the scene. I then am a viewer and I put my VR headset on. And as you're going to see, she's going to move in a position the camera never was. She steps forward, she bends over and leans down. She's looking at positions in the scene the camera was never there to capture. But because of the quality of depth information, the resolution and the arrangement of the physical hardware of the camera, and the quality of the computer vision code on the back end, we're able to recreate views that didn't exist before, to give you that sense of immersion, like I can move around and be in that scene. This is what we mean by really immersive video context. We're going to get these cameras into people's hands this year. We're working with a wide variety of partners. We've learned a lot in the last year about how filmmakers like to produce in the real world. So this camera is designed to work with your tool chain. No lock-in to any proprietary back-end system. Use your tool of choice. It's rugged, field serviceable, portable, and we're going to work with partners to make it easy for people to buy or rent these cameras. This is X24 and X6. Now, VR, even though we're shipping products and there's lots of awesome stuff happening, is on our 10-year roadmap. So I often get questions. It's like, hey, people are buying VR headsets. Why is it in the 10-year category? And it's in the 10-year category because we're far from our goal. Michael Abrash, last year in his keynote, talked in detail about how far away state-of-the-art VR headsets are from the limits of the human perceptual system. You can see VR today at the top and what your eyes and ears can perceive at the bottom here. And we have quite a ways to go to get to that point of full immersion. But the good news is we have line of sight to most of these problems. We're working hard in Oculus Research and others to build systems that can solve most of these problems. But this is just the input side. And Michael Abrash is going to talk a little bit later today about where we're going with both VR and AR. But there's another part of this, which is how I get input from me into the VR world. And Oculus Touch is the state-of-the-art, best experience you can get to get your hand motions into VR. But I'd ask you, what happens if you could skip that step and directly go from your brain to input into the VR system? Now stay with me. I know this is a little out there. But luckily, Regina Dugan is going to talk a little bit later today about amazing advances happening in the field of brain-computer interfaces, actually being able to read signals from your brain and input them directly into one of these systems like a VR system. And it has amazing applicability for AR and VR. And I can't wait to hear her talk on this later today. So that's it. Wanted to frame up our 10-year vision, connectivity, AI, and VR and AR. We have a lot of great, awesome content that I can't wait to see coming up next after this, starting with Yale McGuire, who's going to talk to us in more detail about our connectivity efforts. Thank you all, and welcome to day 2 of F8.
Thank you, Shrep. Community. They come in all sizes and across all regions. But being able to give people the power to make communities global depends on connectivity. Not all these communities can be connected via traditional methods of connectivity today. We started our connectivity efforts at Facebook to change that. We really want to focus on connecting everyone. Our mission is to develop next-generation technologies that can bring down the cost of connectivity by an order of magnitude so we can reach the unconnected and improve price, performance, and speed for everyone else. If we think about a landscape where some people live in cities and some people live in rural communities, connectivity starts with fiber. But it doesn't end there. Fiber is the backbone. But if you think about trying to connect a rural community of 400 people or every city block in a dense city environment, fiber is not the solution to get there. It's too expensive. It takes too long to develop that technology and get it out to those edges. So we're focused on building blocks that come together to make flexible and extensible networks that combine together to make those networks possible. So our efforts that I'm going to focus on today really focus on thinking about a strategy that focuses on the atmosphere and the stratosphere. As we think about wireless in general, going through the atmosphere, there's a lot of challenges in trying to make this work. So on the one end of the spectrum, which is what our typical smartphones use today, the electromagnetic spectrum covers about 5 centimeters out to about half a meter. And this is designed to be able to make it so that part of the spectrum can go around buildings, can go around people, et cetera, et cetera. On the other end of the spectrum is fiber. You can point it and put capacity exactly where you want. There's tons and tons of capacity. But it's really hard to be able to go through clouds and fog and rain and things like that. So a common theme of thinking about going through the atmosphere and going through the stratosphere is a technology we call millimeter wave. This is an ideal space between those long wavelengths, literally in the millimeter wave, and lasers, and those give us the ability to make it so that you can put capacity exactly where you want it, but it allows you to go through clouds and rain and everything that exists in the atmosphere. So we're going to talk about 2 milestones that we've reached today, and the first is literally happening behind us in the city of San Jose. So before we start there, I want to provide an analogy to think about intuition for developing systems for communication. So with that, I want to give people a sense of an analogy by thinking about the light you can see, not the light that you can't see that comes from your mobile phones. So think about your favorite city that you're walking through. It's a bright, beautiful day. I had this experience myself when I was walking the city of San Francisco on Saturday morning. The sun is beaming down, and I'm appreciating the warmth that I'm experiencing around myself. I walk under a tree, and it gets darker. I look down a city street, and it's darker as well because the light is being occluded by buildings around me. I appreciate the beauty of that cityscape, the contrast that exists between light and dark. But in the world of wireless, that cityscape of beauty is not what we want. If we visualize that in the electromagnetic spectrum, we actually want brightness everywhere because darkness are dead zones. That's not the speed that we want. We want brightness everywhere because speed is brightness. And so if we think about this analogy and what we want to do in developing cities and connectivity, we want to think about not just having fiber go to every building that would create that brightness everywhere, but can we think about ways in which we can extend that fiber to make fiber literally wireless. And so that is the idea behind Terragraph. It's a really simple concept of trying to extend fiber wirelessly using millimeter waves, but doing it at scale in a city has never been done before. So we've designed the system to be consumer level in pricing. It's custom designed in hardware and software by Facebook, and it's designed to be deployed by mobile operators in the future. And it uses a portion of the millimeter wave at 60 gigahertz. This is 12 to 25 times faster than a traditional Wi-Fi access point. But because this has never been done, there are a number of challenges that we have to work through. So let's get into the first one. The traditional model of thinking about trying to deploy all these nodes across a city infrastructure is answering the question, where do you put them? How do you make it so you can get these fiber-like systems where you can point and put capacity exactly where you want, anywhere in a city, such that you can get brightness everywhere? So the traditional model is someone gets into a bucket truck, they get out a telescope, and they look around and they try to identify the next site. And you keep on doing that until you build up that entire network. That can take weeks to months at a time. It's too long, and we wanted to think, is there a way in which we can fully automate this process? Fortunately, our computer vision team was up for the task. They wanted to think, can we have machines replace those systems of people looking through objectives to build that network automatically? Now, Shrep talked about our awesome computer vision and AI teams, and so we gave them this challenge. Can you figure out how to deploy in an automated fashion the visualization to connect an entire city grid? And so they said, sure, get us a high-resolution 3D map of an entire city. So we're able to do that. You can get self-driving cars and drones, and they can build up that image. The next task was figuring out where to put the infrastructure, and so this is where the magic starts. So here's the 3D visualization of that, and you can see the city of San Jose literally behind us being mapped out. Computer vision pipeline is able to start to segment that system into buildings, and then we get poles, and then ultimately all the line of sight paths. So what used to take days to months at a time now gets reduced to hours. And the system is able to find paths that no human was able to ever discover before. So it's pretty awesome to see that coming together. The next challenge that we faced was how to make the system resilient. So in a cityscape, the world is very dynamic. Somebody may be cleaning windows on a building. There may be a construction project that's happening. In the springtime, leaves may grow on trees and get in the way of that laser-like capacity. Or a tall bus might drive by and break a connection. So in a dynamic city, you have to make sure a system like Terragraph is able to be resilient across all of those changes, and to make sure that it's fault tolerant and providing capacity no matter where you are, so that brightness is always there and it's constant. And so rather than get into the technology behind this was another team that was up for that challenge, our network engineering team, and they developed this protocol that allows you to route as these dynamic events are happening in the city. We want to show you just a little demonstration of that happening just literally behind us in San Jose. So what I'm going to do is, this is a little bit of a challenge. This is the network. This is the building that we're in right now, the City National Civic Center. And the green spot is where we wanted to shoot a live video. So imagine that you're just walking through the city and you see something hilarious on the street, and you want to capture that and share it with your friends. Ultimately, you want this to be a 360 3D video in the future. You want to make sure that you don't care about how many signal bars you have on your phone, that no matter where you are in a dense environment, you're able to connect and share that experience. And so that's what we wanted to do here. So this is a live video of something that some people captured, and it was streamed live on the Terragraph network just a few days ago. And so what I want you to do is to see if you can see anything that changes in the network while we actually break the network and change it and allow it to reroute in a time that's faster than human scales. So that's what those nodes are. Each one of those blue boxes represents a Terragraph node. And you can see the connection that exists between fiber and the green spot, which is where this video site is taken. So what I'm going to do is I'm going to count to 3, and I'm going to challenge you to look at that video and see if you can see anything that goes wrong. What I'm going to do is I'm going to look at this and indicate when the network actually changes over. OK? So are we ready? 1, 2, 3. Look. I told you it was hilarious, right? OK. Blip. Did you see anything other than this hilarious scene? Did you see anything go wrong with the video? OK, let's actually do this again. We're going to go 4 times slower, and let's see if we can see any artifacts. And we're going to zoom in time. There, it changed. OK, I sort of tricked you. Nothing actually happened. This was just a video that streamed over the Telegraph network, and it just worked. And that's the point. Anywhere you go in a city, we just want to make it so you don't care about how many bars you have. You are just connected. So let's get out of, thank you. So let's get out of the city and head to the stratosphere. Now imagine you could take this screen and scale it up 1,000 times. The current technology for doing that is going to space, literally a geosynchronous satellite, and trying to connect to people in rural communities. And we know that roughly 99% of people live within a few hundred kilometers of cities and fiber. So we thought, is there a better way? Can we go to the stratosphere, 20 kilometers in the atmosphere, and try to connect that way? So fiber connects to a microwave dish, a millimeter wave dish, provides connectivity to the first plane, and then other millimeter wave systems or lasers can interconnect and form a network in the sky. So it's a cool idea, but parts of it we've actually started to do. So this is our Aquila system. This is a flight from last year. And to me, this was one of the most incredible moments in my life, where I got to see an aircraft, roughly the wingspan of a Boeing 737, the mass 1/3 of a Toyota Prius, running on the power of 3 blow dryers, flying in the air for an extended period of time. But this is not a communications network yet. It needs connectivity. It needs a millimeter wave system. And so we scoured the Earth and tried to find, is there a technology that can go in this aircraft today? And there wasn't. So we had to make a system that was 10 times faster and roughly 10 to 100 times less in terms of mass and power. So I'm really excited that last year we announced that we achieved, over a 13-kilometer link, a 20 gigabits per second millimeter wave link. It was a pretty awesome achievement by our team. Well, that's old stuff. This is the future. And I'm really pleased to announce that using that same link, the team almost doubled that rate and achieved 36 gigabits per second over that link. So we beat our own world record. We then flew it in a Cessna on the path to getting it into an Aquila, and we achieved 16 gigabits per second in that system. And then I mentioned optical links that may exist between aircraft, and we actually have built an optical link also on the same 13-kilometer path, and we achieved 80 gigabits per second. So we're really, really excited about that progress. And to put that into context, imagine streaming 4,000 ultra-high definition videos simultaneously. That's what we're able to do with the fastest system that we had available today. So it's a pretty cool and awesome achievement by our team. So I'm really, really excited about the millimeter wave and laser technology that we're designing for Aquila. And we hope ultimately that systems like Aquila existing in the stratosphere will provide backhaul technology to other component technology like OpenCellular. But we didn't want to stop there, because we were thinking, once we originally came up with this idea of Aquila and high-altitude platforms, we thought it would be super cool to be able to have networks in the sky that can be there persistently forever and provide connectivity to people on the ground. But there was another use case that we're really passionate about. As we talked to people in the telecom community, there was a lot of interest in thinking about times of crisis, when connectivity becomes crucial. And we were interested in the idea that could you deploy infrastructure instantly when these times of crisis happen? Tower infrastructure may be destroyed. There may be fiber in the ground, there may be power, but there may not be the means by which we can actually connect people. And one of the things we were really excited about Aquila was that it's a plane. You can take it up into the stratosphere, you can bring it down, and you could deploy it very, very quickly. But the timelines in terms of developing this technology, from a regulatory perspective, all the engineering challenges we have to do, it could take up to 10 years. And we still love this use case, and we wanted to think, is there a way in which we can try to address this problem faster? And we started to think about the nature of what connectivity was and the fact that connectivity usually starts, especially in rural contexts, from towers. You have to get up to a certain height to make that brightness spread around. And we started to think about towers themselves, and could we reduce them to their fundamental essence? And so this idea of something we call a tether antenna was born. We wanted to reduce the tower to something that was just as simple as a single cable that could be deployed instantly. And we call this a type of infrastructure. So I'd like to show you a little demonstration of that. So the basic idea is that you tether to fiber and power on the ground, and you take that single cable and lift it into the air hundreds of feet with a helicopter. This helicopter, you can see, getting a sense of scale, is roughly the size of a VW Bug, but its mass is that of one of those tires. And the idea is that it can just lift off. As you see, there's a winch attached to the helicopter, and it just takes that tether up and stays there. There's lots of challenges we have to work out. It's a high voltage system that has to support kilovolts of power that go up through the tether. It has to survive through very high winds. We have to avoid things like lightning. There's lots of challenges ahead, but we're really excited about the notion of this tether antenna system. It's operated for up to 24 hours, continuously so far, and we expect for months at a time, it's going to be able to provide connectivity to people who most need it. So these are some of the projects that we've been working on. Some projects like Terragraph, we expect, no pun intended, are around the corner. And others like Aquila are going to take up to 10 years to develop. But we hope tether antenna is something that's just a few years out to be able to provide connectivity for people who really need it. If we're going to give people the power to build communities that work for everyone, it starts with building connectivity that works for everyone. So thank you, and I'm going to hand it off to Joaquin.
All right, welcome everyone. I want to take you on a journey of how deep learning has transformed the ability of computers to understand videos and images, and how we are taking AI out of the data center and into the phone to build amazing new visual expression tools for everyone. In less than 5 years, computers have gone from only being able to make the same judgment about all the pixels in an image to being able to understand every single pixel individually. Take this example here of a photo of two of my colleagues and I. The computer doesn't only know that a blue pixel corresponds to a person, it can actually tell which of the three of us it belongs to. In this example, all of this is powered by MaskRCNN, which is a new deep learning architecture developed by the Facebook AI research team, which simultaneously detects, classifies, and segments objects. The cool thing is that it is extensible, and the team has also applied it to estimating human pose. It achieves state-of-the-art accuracy at these 4 tasks, and it is so computationally efficient that we can very easily run it on videos, and I want to show it to you. OK, you can see it picks up this person walking in the background. It also detects someone walking towards us, and although the table is hiding part of my body, the algorithm is robust and still can estimate when I'm sitting, standing up, and walking. Now, as much as I love watching skeletons being tracked in a video, we still don't know what the full story is here, right? But the good news is that we're working on it. We are building a multimodal video understanding engine that uses several AI algorithms to recognize and tag people, to identify the actions they're taking and when, and to understand the words that are said, transcribe them, and also translate them to other languages. Let's check it out.
Let's get some coffee.
Oh yeah, let's get some coffee. All right. Now we know what the story is here. So what happened is that Rina noticed that Merlin, Manohar, and I were not looking energetic at all, and she had this great idea just to go and take us out for coffee, right? Now, 50% of our community does not speak English, like my dad, who lives in Madrid. But thanks to the translation provided here, Now my dad is reassured that I have friends who take me out for coffee. Now, imagine building an AI system to understand what actions are happening in a video and when. It's very hard to do if it treats the video as a sequence of independent frames, which is why the team has built a new neural network architecture that does 3D spatiotemporal convolutions using time as a third dimension. And this is what we use here to understand when is it that we were sitting, when did we stand up, when did we wave, and then when did we walk. But this was only one video, right? On Facebook, every day, people watch over 100 million hours of video. And by the time I am done with my talk here today, there will be over 100,000 new minutes of video available to me. Now, luckily, our algorithms crunch over 1 billion frames of video every second. And because they can identify what actions are going on and when, if I want to catch up on that old Real Madrid game, I can jump straight into the action. And look at that, enjoy that, whoa, phenomenal goal. So awesome. All right. The cool thing is that we have integrated our video understanding algorithms into the Facebook AI platform, available to all product teams across the company to build awesome new video experiences. I want to spend a couple of minutes on the AI platform. A couple of years ago, we took a bet to weave AI into the engineering fabric of Facebook. And today, the AI platform has brought together a vibrant community of AI experts and non-experts, fostering amazing collaboration all the way from research into product. Now, this is only half of the story. Traditional deep learning frameworks have been optimized for the desktop and for the server, but we, at Facebook, believe that AI should not be confined to the data center, which is why this past year, we've built a new deep learning framework called Caffe 2. It is designed to be maximally efficient, both on the data center and on the phone. Developers write exactly the same code, and the framework optimizes it for the target architecture. We have integrated Caffe 2 into the AI platform of Facebook. And on the server, our computer vision systems can now process 10 times more images and videos per day. And on the phone, we were able to speed up neural style transfer by 100 times, making it possible to run locally and in real time. But we see this only as the beginning of a journey, and it's a journey that we're not taking alone. I'm incredibly happy that we have open-sourced Caffe 2 for the community, and that we're doing this with the support of our partners, including Amazon, Intel, Microsoft, NVIDIA, and Qualcomm. All right, so now that we have Caffe 2 on the phone, we are building the world's largest AI-powered camera, bringing amazing new visual experiences to billions of people on Instagram, on Messenger, and on Facebook. So if you pause and think about it for a second, this is one of the world's largest AI deployments ever. And one thing that I love about using AI here is that you can actually take features that were only available in the highest-end devices and make them work essentially on any phone. And I'm going to walk you through a detailed example here around depth effects. I want you to close one of your eyes for a second, or cover it. The truth is that you technically can no longer perceive depth, but your brain still does an amazing job at guessing how far different things are from you. And the reason is that you have accumulated all this experience living in the 3D world. Using that same principle, we have trained an AI algorithm that takes a single flat image and approximately reconstructs its depth. Let's see how it works here. All right, you can see that on that outdoor scene of the Great Wall of China. It can kind of figure out what's going on. We have an indoor shot of a library. And hey, it even works on that old photograph of a moon landing. So cool. Just like when you covered one of your eyes, the majority of phones only have one camera. And even if you have a high-end device with two cameras in the back, if you use it in selfie mode, you're back to one single camera. This inspired us to take our depth estimation algorithm and bring it to the phone. Let's see what we can do with it. Here you see Orion from the team, and we're taking a portrait of him. The algorithm is dynamically estimating what is foreground and what is background, keeping the subject in focus and giving us a control we can use to blur the background as much as we want to create that beautiful illusion of depth. Now, flip the phone, put it in selfie mode. Here's Anshul from the team as well, and he's doing the same moves. Now he's going to go ahead and blur the background, but he's not happy with that frame. He's still trying to find the right shot. And you can see that dynamically, the background is being recomputed and reblurred. All right, that was the right shot. Good job, Anshul. All right. I absolutely love how we can use AI to bring advanced features essentially to any phone in any mode. But what we've talked about so far was what we can do when we're given one single flat image. And if you remember, just a few minutes ago, Shreb talked about the Facebook Surround 360 camera with its 24 cameras that allow us to capture an entire 360 scene in 3D with multiple perspectives on the same pixel. Now, you might get a little bit worried here, and you might say, well, I just don't own one of those, and if I did, it wouldn't fit in my pocket. That's okay. We've got you covered. We are working on algorithms for casual 3D capture, where you can do this simply using your phone. And I want to show this to you applied to a scene that we've seen before. So remember this? This is where it all started. Here we are. I can use my phone now like a time machine, travel back to that instant, and explore the scene from different angles. And importantly, go looking for that one feature that I missed, which is that my friend Ari dropped a little something for me there. Oh, look at that. Yes. Yes, a can of my favorite IPA. All right, Ari, you're awesome. I'm definitely going to enjoy this After Effects. It's been an absolute pleasure to be here with you today to talk about how we are taking AI out of the data center and into the phone to build the world's largest AI-powered camera. And with Café 2, we're doing this together. All right, and now it is my pleasure to introduce the Chief Scientist of Oculus Research, Michael Abrash. Thank you, everyone.
Good morning. Over the last 2 days, we've seen a ton of really cool camera-based AR, and that's been pretty awesome. But it's just the beginning. As Mark said yesterday, we all know what we really want, AR glasses, and that's what I'm going to talk about today. They aren't here yet, but they're on the way, and when they arrive, they're going to be one of the great transformational technologies of the next 50 years. I was lucky enough to be there at the start of the last great computing revolution, and believe me, we're all in for an amazing ride. More than 3 decades ago, I was a PhD student in energy policy at Penn. I was actually a lot more interested in programming, but this was the era of oil embargoes and energy crises, and energy was where the jobs were. I was trying to come up with a dissertation topic, but I wasn't getting anywhere, mainly because after 3 years of studying energy policy, I was bored stiff. Then the IBM PC came out. I wanted one, but a PC with a printer and 128K of memory cost $6,000 back then, and you could get a new car for $6,000 in those days. So I needed a good rationalization for spending all that money. Fortunately, one of the reasons I hadn't made any progress on my dissertation was that I had written a video game for the CPM computer I used at work. So I told my wife that if I got a PC and I ported my game to it, I was sure it would sell a lot of copies and I'd make a lot of money, and she said, okay, go for it. I got the game done in 3 months by continuing my disciplined program of not writing my dissertation, and I sold it to a publisher. Here's what it looked like. Trust me, that was totally cool in 1982. When the first royalty check came and more than paid for the computer, I dropped out of the PhD program to write games for a living, horrifying my mother, who was convinced I had made a career-ending mistake. I'm pretty sure she's okay with it now, but honestly, she had a point. Writing video games wasn't even a real career back then, and in fact, although I wrote 3 more games, that was the biggest royalty check that I'd ever see. It didn't matter, though, because I had the good luck to change careers right at the beginning of the personal computer revolution. And as a result, I've had the opportunity to work on an amazing range of interesting stuff, including operating systems, games, consoles, graphics software, CPUs, GPUs, and virtual and augmented reality. I admit it's a big step into the unknown to jump into a technology wave just as it's starting, but the possibilities it opens up are limitless. And one thing I can honestly say is that I've never been bored. You, too, need never be bored, because a new wave, which I'll call virtual computing, is just starting. Virtual computing encompasses both virtual and augmented reality, and I think its impact may ultimately be even greater than that of personal computing. 20 or 30 years from now, I predict that instead of carrying stylish smartphones everywhere, we'll wear stylish glasses. Those glasses will offer VR, AR, and everything in between, and we'll wear them all day and use them in almost every aspect of our lives. The distinction between AR and VR will vanish. The real and virtual worlds will just mix and match throughout the day according to our needs. In the nearer term, due to technological constraints, AR and VR will follow separate paths toward that mixed reality future. VR will offer increasingly convincing experiences, and it will gain the ability to capture the real world and bring it into your virtual world. That will let you move around safely, use your keyboard, mouse, and desk in VR, pick up your coffee mug, teleport all over the world, and share experiences with people all over the planet. VR will be the most immersive way to interact with the virtual world, and it will revolutionize how we work and play. Bright as the future of VR is, though, and knowing what my team at Oculus Research is working on, I'd say it's very bright indeed. There's one key area that will never be VR's strong suit: always on, go everywhere, mixed reality. Because no matter how good VR gets, few people would be comfortable socializing in person with someone whose eyes they can't see, and social acceptability is an absolute requirement for anything we wear in public. In order to make virtual computing as much a part of everyday life as the smartphone is today, we're going to need see-through augmented reality, transparent glasses that can show virtual images overlaid on the real world. See-through AR glasses are the path to what I'll call full AR, augmentation that enhances your vision and hearing seamlessly, that makes you smarter and more capable, that is light, comfortable, stylish, power efficient, and socially acceptable enough to accompany you everywhere you go. And full AR is what I'd like to talk about today. Now, I'd love to start off by showing you cool demos of ultra-light, ultra-powerful AR glasses, but one of the problems of looking into the future is that it doesn't yet exist, so that will have to wait for another day. My objective today is to put AR glasses on your long-term radar. It may take 5 years, 10 years, or even longer, but eventually they will become a vital part of our everyday lives, and that will create tremendous opportunities for everyone in this room. In order to understand why that's so, let's take a quick look at the last great fundamental change in our relationship with computers and information. It all started with this man. Raise your hand if you know who this is. That's the usual response, which is a shame, considering that JCR Licklider, universally known as Lick, is the single person most responsible for the information-rich, interactive world we all live and work in today. He was a psychologist at MIT in 1956 when he encountered Wes Clark's TX2, which was, in some ways, the first personal computer. Although, as you can see, it didn't quite have the form factor we're used to, especially since that's just the console. Those are the memory banks. They were so large because they stored a huge amount of data, nearly 300K bytes. In addition to its immense storage, the TX2 had a 1K by 1K graphics display and a light pen, and critically, it supported direct real-time interaction, something new and special in an era where you drop your card deck in a bin and come back hours later to get the printout. When Lick saw the TX2, he had a vision of human-oriented computing, in which computers would interactively amplify the intelligence and decision-making capabilities of humans. Lick planted the seeds of that vision at ARPA in the 60s, conceiving what he called the intergalactic network, which evolved into ARPANET and then the internet, and funding a variety of research into interactive computing, including Doug Engelbart's work that led to the mouse and GUIs. Many of the people he funded went on to join the Xerox Palo Alto Research Center, Xerox PARC in the 70s, where, as I'm sure many of you know, the pieces of human-oriented computing that Lick had nurtured came together, and the personal computer as we know it was born in the form of the Alto. So it was 16 years from concept to first fully functional prototype. It would be another 11 years from prototype to the first mass-market human-oriented system, the Macintosh, and then 2 decades more before human-oriented computing reached 1 billion people. But once the Alto showed what was possible, the revolution had begun. That long rising wave of human-oriented computing, from one man's vision to an indispensable part of the everyday life of billions of people, is worth keeping in mind as we think about the future of AR. Today, thanks to Lick's vision, we're able to dip into a vast ocean of virtual information and connections wherever and whenever we want, through two-dimensional surfaces that surround us and accompany us everywhere we go. There are portals to the virtual world on our desks, in our laps, in our living rooms, in our cars, in our conference rooms, even in airplanes. And of course, every one of us here today has a virtual portal in our pocket or purse. There's probably not a person in this room who's more than 10 seconds away from the virtual world right now. And for most of us, that's true almost every waking moment of our life. Each of us has instant access to better communication and many orders of magnitude more information than anyone in human history. And yet, we can do so much better. Rather than looking at that virtual ocean through windows, we can swim in it like fish. And that's what AR is all about. So what would it take for us to live in the virtual world? Well, everything we experience in the world, real or virtual, comes through our senses. So it seems obvious that we'd want to be able to see, hear, feel, smell, and taste the virtual world, just as we do the real world. If we could do that, the virtual world would simply become a part of our reality. VR shows that it's already possible to put the right photons on our retinas, the right pressure waves on our eardrums, and the right vibrations on our skin to get the full perceptual system to kick in, creating experiences that feel genuinely real. If we could mix those virtual experiences seamlessly with the real world, AR would then be able to leverage all our perceptual, memory, cognitive, and motor capabilities. In short, all the ways we're wired to interact. And then we would truly live in the virtual world. It's encouraging that we already have the ability to create VR experiences that feel real, and you'll know how powerful that can be if you've ever looked over the edge of a virtual drop-off. However, the true breakthrough will come when the real and virtual worlds can mix freely, wherever we are, whatever we're doing, so that the virtual world simply becomes part of our everyday reality. That will require AR glasses, and those will be much more technologically challenging than VR headsets. In fact, the set of technologies needed to build them doesn't yet exist. But once AR glasses do get good enough, AR has the potential to enhance almost every aspect of our lives. What exactly does that mean? Well, consider the glasses I'm wearing. They enhance the acuity of my vision every waking moment. But what if they were AR glasses that enhance perception in other ways as well? What if they could enable me to see in low light? What if I could see people and places on the other side of the world? What if AR glasses could help me live a normal life if macular degeneration, which runs in my family, hits me? But that's just the start. What if the glasses also enhanced memory and cognition? Imagine if they could feed you key statistics in a business meeting, translate signs on the fly, and prompt you when you can't remember someone's name. Imagine glasses that let you and a coworker pop up a shared whiteboard in a cafe. Share that whiteboard with a colleague in another city and let you bring up your full workspace in complete privacy on a plane. Imagine they could help us make healthy food choices and tell us whether a loved one had a fever. Imagine they could even mute random background noise so we can concentrate, which I personally would love, but still let us hear a friend's voice. And, of course, imagine glasses that do everything that smartphone AR does. Stickers, face filters, style transfers, location-based information, sticky notes, and all the rest, but seamlessly and continuously. Imagine, too, that they let us create and share inexpensive digital goods, play games with friends around the world, share private notes and art, get interactive repair advice, and on and on. Most of all, imagine that they let us transcend time and space to connect with those we care about. In short, imagine AR glasses that enhance our perception so that the lines between the virtual and real worlds blur, giving us deeper experiences, stronger connections, and richer lives. All that and much more is what AR is going to be about. I can't tell you the most important ways in which AR will change our lives. any more than I could have told you 15 years ago that the single most popular use for smartphones would be staying connected with friends and family through Facebook, or that using them to summon ground transportation would be a standard part of travel, because neither application even existed at the time. But I have no doubt whatsoever that similarly ubiquitous and indispensable AR applications will arise once the AR platform exists, and people with AR glasses will simply be the smartest, most productive, best connected people around. That's quite a claim, but remember that we've already seen it happen once in the form of human-oriented computing. Think about how much smarter and more productive and connected you are thanks to your computer and phone. And unlike human-oriented computing, which was a lonely quest for many years, the enormous long-term potential of AR glasses is already obvious, as Mark pointed out yesterday. Oculus research is hard at work on AR, and we're far from the only ones, which is why I believe that unless AR glasses good enough for broad consumer use are literally impossible, which I doubt, they will become a reality in the not-too-distant future. Which is not to say that they're right around the corner. Despite all the attention focused on AR today, it will be 5 years at best before we're really at the start of the ramp to widespread glasses-based augmented reality, before AR has its Macintosh moment. And even once we're on that ramp, it will take many years to fully realize AR's potential, just as it took decades for human-oriented computing to mature and reach billions of people. So, what will it take to get AR glasses on the ramp to being as ubiquitous as smartphones are today? First, let me say that I think we will ultimately need to get to full AR in order for that to happen. If you'll recall, I defined full AR as glasses that enhance your vision and hearing seamlessly, that make you smarter and more capable, and that are light, comfortable, stylish, power efficient, and socially acceptable enough to be a constant part of your life. Full AR will not be an occasional or special case device. It will be your always-on helper, continually aware of your surroundings, your context, and your history, constantly mixing the real and virtual worlds to serve your needs and keep you connected. As a simple illustration, consider my earlier example of AR helping us remember people's names. That would surely be useful. I've had the embarrassing experience of forgetting the name of someone I've met before. But do you really want to be seeing thousands of people's names floating over their heads right now? Of course you don't. But you also don't want to have to submit a query every time you do want to know a name. You just want it to pop up when you need it, the same way your own memory works. And that will take always-on, contextually aware AI to make it happen. Think of full AR as being like having a tiny, tireless assistant with a perfect memory and an internet connection sitting on your shoulder, answering your questions and feeding you useful information by beaming it directly into your eyes and ears. Getting to full AR will require major advances in multiple areas. I've listed the broad categories here, but considerable research and development will be needed in many other disciplines, including material science, perceptual science, and graphics, to name just a few. Seeing virtual images is the first thing people think of when they think of AR. There's a lot that has to be solved in order for that to be good enough, including resolution, field of view, depth of focus, image quality, see-through quality, brightness, and contrast. And it's far more challenging than VR, because we have to see the real world clearly, and we have to be able to wear the glasses comfortably all day. Augmenting audio is similarly challenging, again, because of the need for comfort and to be able to hear the real world clearly. People tend to think AR is all about the glasses, and particularly virtual images, but there's a great deal more to achieving full AR's potential, starting with interaction. AR's interaction model will be very different from anything that's come before, because you have to be able to interact in all the situations you encounter during the day, with your hands full, in noisy environments and meetings, you name it. I predict that AR will involve the greatest leap in the nature of human-computer interaction since the mouse and GUI. The ultimate would be a direct brain-computer interface, and as Regina will tell you in a few minutes, that may be closer than you think. Computer vision is obviously needed in order to precisely localize the glasses, so that virtual objects can be properly combined with the real world, but that's just a fraction of the importance of machine perception to AR. In a much more general sense, before you can mix the real and virtual worlds effectively, you first have to know what's out there in the real world. The more capable AR glasses become of reconstructing and understanding the world around you, the better they'll be able to mix virtual with real, and the more relevant the information and advice they'll be able to provide you will be. That leads directly into AI, which is where all this technology comes together to make you smarter and more capable. That tireless assistant sitting on your shoulder throughout the day will require more general AI capabilities than anything that exists today. And in fact, it may be augmented reality that drives AI to the next level. All these technologies have to be packed into a system that meets the requirements for an always-on, all-day, go-everywhere experience: weight, power, thermals, comfort, form factor, social acceptability, and so on. And that will be an even greater challenge than building the first smartphones. Finally, the payload for all this is the experiences you'll have with your newfound superpowers, and that will be a rich area to explore for a long time. So, how far along is all of this? Honestly, every area I've discussed requires technology that's beyond today's state of the art. Full AR is roughly at the point where human-oriented computing was in 1971, when the pieces of the personal computer were just starting to come together at Xerox PARC. The AR equivalents of the mouse, the GUI, bitmap graphics, and all the rest are still being figured out. In my opinion, every single one of the challenges of full AR will have to be solved before augmented reality can become an integral part of the lives of a billion people. But we'll see a lot of less than full AR before then, such as glasses with heads-up displays, audio-only devices, and cumbersome headsets designed for enterprise applications. And, of course, as we've seen over the last 2 days, camera-based AR is already exploring the potential of mixing the real and virtual worlds. Also, as I mentioned earlier, it's also possible to come at AR from the other direction, by capturing the real world and then displaying it in VR, and I expect that to be an important part of the virtual reality experience before too many years pass. So we'll see many varieties of AR over the next few years, and that will help map out the space of AR experiences, but the tipping point will come with full, always-on, go-everywhere, audio-visual AR glasses. That will certainly take 5 years, and could well take 10 years or even longer. At least that's my opinion, although I would be delighted to be proven wrong. But that day will come, and when it does, it will change the world as completely as LixVision has, and maybe even more. You and I, all of us here today, are incredibly lucky. We're getting to play an important part in the great wave of human-oriented computing that Lix set in motion 60 years ago, helping to connect the world and make all the knowledge of humanity instantly available. We get to transform the way the world works, plays, communicates, and interacts. That's good fortune enough for one lifetime, but there's even better yet to come. The next great wave, virtual computing, is just beginning to form, and it will complete the transformation Lix started by making us natives in a new world, one that combines the best of both real and virtual, a world in which we have tightly coupled superpowers of perception, a brilliant, tireless assistant always ready to help us, and the ability to effortlessly transcend time and space and connect with one another. That wave is still far from reaching us with its full force, but keep an eye on it, because one day, before too long, virtual computing will change everything. And when it does, you will have the opportunity to be an important part of that change, if you so choose. And if you do, I promise, you'll never be bored. Thank you. And now it is my great pleasure to introduce the head of Building 8, Regina Dugan.
In my entire career, I've never seen something as powerful a force in the world as the smartphone that didn't also have unintended consequences, sometimes grave, sometimes everyday. If we intersect this device with the mission of Facebook, we find that this little black box has allowed us to connect to people far away from us, to share moments of our lives, and to do so unconstrained by time or distance. But it has also cost us something. It has allowed us to connect to people far away from us, too often at the expense of people sitting right next to us. We've all begun to feel it. We don't talk about it much because most of the discussion goes like this. If you were just strong enough, if you had enough willpower, you would put down that addictive drug that is your smartphone and honor the conversation in front of you. Usually this is said in a moment of anger or judgment. But that's the wrong narrative, and it's a false choice. This device is important. It allows us to be curious about the world beyond the one we can see right in front of us. It allows us to have empathy for people we might not otherwise know. It allows us to be adventurers and explorers, humanitarians, and citizens of the world. That's good. It's just that we know, intuitively and from experience, that we'd all be better off if we looked up a little more often. Now, voice interfaces have attracted much attention of late. Voice is referred to as the new type of OS. It's convenient, that's true. It reduces complexity, that's also true. I think that voice is important, but not for these tech-centric reasons, rather for a decidedly human reason. Because these new hardware platforms have enabled us for the first time in a long time to crawl out of this little black box and be back in the room where our lives are and where so many of the people we care about exist. Now, when viewed in this way, we realize that we've only begun to scratch the surface of what's possible. There's much, much more to do. So today and tomorrow, this is our goal at Facebook, to create and ship category-defining consumer products that are social first, to do so at scale, and to power this with a breakthrough innovation engine modeled after DARPA. Products that recognize we are both mind and body, that our world is both digital and physical, that seek to connect us with the power and possibility of what's new, while honoring the intimacy and the richness of what's timeless. Products that refuse to accept false choices. So let me give you an example of what I mean. Let's start with your brain. Your brain has 86 billion neurons that fire 1,000 times per second. Now, they don't all fire at the same time, so let's decrease that by a factor of 100. That would mean your brain is capable of producing about 1 terabit per second. About 40 HD movies are streaming in your brain every second. Now, if you haven't had your coffee yet, you might be moving about 10 times slower, so let's just say it's 4 HD movies every second. And herein lies the problem. How do I get all of that information out of my brain and into the world? What are my choices? Well, I'm speaking to you right now, and I'm transmitting at about 100 bits per second. That's the bandwidth equivalent of a 1980s dial-up modem. So, here's what we have. 4 HD movies per second streaming over a 1980s dial-up modem. Speech is essentially a compression algorithm, and a lossy one at that. That's why we love great writers and poets, because they're just a little bit better at compressing the fullness of a thought into words. So, what if you could type directly from your brain? It sounds impossible, but it's closer than you may realize. And it's just the kind of fluid human-computer interface needed for AR. Even something as simple as a yes-no brain click would fundamentally change our capability. A brain mouse for AR. The woman in this video has ALS. She is completely trapped inside her body. She cannot move or speak, but she is typing with her mind, not with eye blanks, with her mind. An array of electrodes the size of a pea has been implanted where her brain would normally control her motor functions. The electrodes record her neurons firing when she imagines moving the cursor. Then the computer learns to move it for her. Using this system, she can type 8 words per minute. She is typing at 8 words per minute directly with her brain. Now, that's less than 1/3 the speed that you can type on a smartphone, but it is lightning fast compared to silence. So what if instead of using imagined arm movements, we could decode speech directly? Now, to be clear, we are not talking about decoding your random thoughts. That might be more than any of us care to know. And it's not something any of us should have a right to know. Think of it more like this. You take many photos, you choose to share some of them. Similarly, you have many thoughts. You choose to share some of them. We're talking about decoding those words, the ones you've already decided to share, by sending them to the speech center of your brain. A silent speech interface, one with all the speed and flexibility of voice, but with the privacy of typed text. Better yet, with the ability to text a friend without taking out your phone, or to send a quick email without missing the party. No more false choices. Now, Marc Chevalier is the lead for this effort. He's a physicist, neuroscientist, and 6 months ago, he had the idea that this might be possible. Today, we've assembled a team of more than 60 scientists, engineers, and system integrators. They specialize in machine learning methods for decoding speech and language, in optical neuroimaging systems that push the limits of spatial resolution, in the most advanced neural prosthetics in the world. And we're just getting started. Together, we have a goal of creating a system capable of typing 100 words per minute, 5 times faster than you can type on your smartphone, straight from your brain. Over the past 3 decades, work in artificial speech recognition has produced powerful tools to decode text from brain activity while people are speaking. This is real data showing the remarkable result of mapping brain signals to text directly. Now, these systems don't currently operate in real time, and what's more, they require surgery, implanted electrodes. And that simply won't scale. So we'll need new non-invasive sensors that can measure brain activity hundreds of times per second and precise to millimeters. And without signal distortions, even as they read through hair and skin and skull. Now, no such technology exists today. We'll need to develop one, and we think optical imaging is the best place to start. Optical imaging may be the only non-invasive technique capable of providing the spatial and temporal resolution we need, and thanks to technological improvements in performance, cost, and miniaturization driven by the telecommunications industry, we have a very big wave to ride. So how do we get optical techniques in the sweet spot of performance, sampling hundreds of times per second and precise to millimeters? We start by filtering for quasi-ballistic photons. Now, if you've ever pressed a red laser pointer to your finger, you know that your whole finger glows red. The reason you don't see the original resolution of the laser pointer is that most of the photons scatter many times as they pass through, flying off in all directions. The photons are diffuse, and diffuse photons won't give us millimeter resolution. Now, due to chance, Some don't scatter at all. These are ballistic photons. If we filtered only for these, we would retain the original resolution of the laser pointer. It's just that there are too few of them to see. Ballistic photons won't give us enough signal. Quasi-ballistic photons are somewhere in between. They scatter, just not too many times. And if we get the trade-off just right, we can get the spatial resolution we need and have enough photons to measure. Okay, so the next problem to solve is speed. Optical techniques are fast, which is good because speech is encoded in the high-frequency oscillations of neural activity. That means we'll need to sample hundreds of times per second to decode them. But today's optical imaging systems, they don't measure neural activity. They measure blood oxygenation, which is a time-integrated sum of neural activity. It is robust, but it is too slow to capture speech. Instead, we will need to measure the neural activity directly by capturing instantaneous changes in the optical properties of neurons as they suck in sodium and spit out potassium. In a few years' time, we expect to demonstrate a real-time silent speech system capable of delivering 100 words per minute. A speech prosthetic, you might say, for patients in need, a step on the path, as Michael said, to making input for AR more natural. A first prototypical system capable of measuring speech-related neural activity non-invasively on our way to a system that scales. That would be crazy amazing. But it's only the beginning of what's possible. It gets better because your brain activity contains more information than what a word sounds like or how it is spelled. It also contains semantic information that tells us what those words mean. In your brain, a cup is not the label cup. It is a man-made object that you can hold in your hand, one that carries liquid for people to consume. Understanding semantics means that one day you may be able to choose to share your thoughts independent of language. English, Spanish, or Mandarin, they become the same. After all, the word cup, or taza, or chabe is just a compressed thought. And if we can make it possible to communicate directly from your brain, what if we could make it possible for you to hear through your skin? You have 2 square meters of skin on your body. It is a complex network of nerves that transmit information to your brain. Braille, invented in France in the 19th century, taught us that people can learn to interpret small bumps on a surface through their fingertips as language. The Tadoma method, developed in the early 20th century, went well beyond Braille. Based on work with Helen Keller, it sought to create a scalable method for children who are both deaf and blind to communicate. As it turns out, the vibrotactile sensors embedded in our skin allow us to interpret complex inputs, the pressure change in a puff of air, the vibration of the vocal cords and on the jaw as language. What you'll observe in this video is a man, deaf and blind, speaking. He is using only the sensors of his hand in his skin to hear, to process, interpret, and yes, even reproduce the spoken words of his teacher. Remember, he is deaf and blind. He is repeating words that he cannot see or hear by feeling them.
Wait just a minute.
Right. A minute.
Did you forget to shut off the water?
From the 1950s until today, what all of these techniques have in common is our brain's ability to reconstruct language from components. We are wired to communicate and connect. As you listen to me now, the cochlea in your ear is taking my voice and separating it into frequency components that are transmitted to your brain. Your cochlea essentially does a Fourier transform, a frequency domain analysis of sound. So what if we could do the same work of the cochlea, but transmit the resulting frequency information instead via your skin? That's Freddie. He leads this project. And that's Frances. She's an electrical engineer. She is not deaf and blind, but she can hear through her skin. She has a system of actuators on her left arm. They are tuned to 16 different frequency bands. Frances currently has a tactile vocabulary of about 9 words. She learned them in less than an hour. The lights indicate the actuators firing, and you'll see that they fire so fast, she must learn to actually feel the words.
Okay, Frances, so let's go through the 9 words we just learned. We'll do some singles and then doubles and then get more complicated.
All right. Drop.
Okay,
White.
good.
Sphere.
Okay. Let's go to 2s.
Yeah. Black sphere.
There you go. Good job.
Throw cube.
Good. All right, let's go to the 3-word sequences.
Yeah. Grass black cone.
Good job.
Grass white sphere.
All right. All right.
Throw white sphere. All right.
It's amazing. If you ask Frances what she feels, she'll tell you that she has learned to feel the acoustic shape of a word on her arm. The word black moves from low frequency regions to high frequency regions. The word blue is more localized. She processes these shapes in her brain as words. She's learning how to use the artificial cochlea we made for her skin. If we put these two things together, they suggest that one day, not so far away, it may be possible for me to think in Mandarin and for you to feel it instantly in Spanish. Imagine the power such a capability would give to the 780 million people around the world who cannot read or write, but who can surely think and feel. Now, despite being much closer than perhaps you realized, these things are still a few years away. And yet, somehow, it feels urgent to us because we don't always have the luxury of time. I once read an article that said 93% of our face-to-face time with our parents is done by the time we finish high school and leave home. Now, most people experience that fact like a kick in the gut. Why? Because it's a profound reminder of the power of connections and that we should do all that we can to increase our sense of presence and connection beyond that remaining 7%. This is my mom. When I moved from the East Coast to the West Coast, I struggled to figure out how to stay connected to her. I tried lots of things, most of them didn't work, and I could feel her drifting away from me. I finally decided that I would try to phone her every day in my car between my house and the coffee shop. It's about 5 minutes. And each week, I got her a little more often than the last, and the nature of our conversation changed. She told me about her begonias, about the latest exploits of her dachshund Chloe, who hides my dad's stray socks in unknown locations. I told her about a talk I had to give that I felt a little nervous about. We actually got closer. Because it's not the big moments alone that define relationships. It is the extraordinary everyday, the beautifully mundane. And I owe the depth of my relationship with my mom in part to technology. Hands-free and Bluetooth made it possible. Those technological advances made it possible for me to be in my life and still connect with my mom. I'm grateful because my mom is awesome. And I thought you might want to meet her, so we flew her in to say hi. She's sitting right here in the front row. It's my mom. Say hi, Mom. I'm optimistic. I'm optimistic that technology can help, that new hardware platforms can chip away at false choices. It's incredibly exciting to do this kind of work. But is it a little terrifying? Of course. Because this matters. Success matters. And so if we fail, it's gonna suck. And the only way to avoid that pain is to do work that doesn't matter to you. And that sucks even more. So why do we sign up to being a little terrified each day? Because that's the price we pay for the privilege of making something great. The risk of failure and that slightly terrified feeling that comes with it is the price we pay for the privilege, the honor of making something new. So be a little curious. Commit to being a little terrified each day. And one last thing. Don't forget to call your mom. Thank you.